frequency response plots. So sinusoidal transfer function is given by sinusoidal transfer function is given by g of j omega, h of j omega. So it has complex in nature, and has both magnitude and phase angle. Expressed as g of j omega, h of j omega, which is nothing but your sinusoidal transfer function, which means that the input applied is sinusoidal. We would like to analyze the response of that. G of j omega, h of j omega has a magnitude g of j omega, h of j omega, and the angle g of j omega, h of j omega. Now it is very simple to see that both magnitude and the phase angle of g of j omega, h of j omega are the functions of omega. Both magnitude g of j omega, h of j omega, and phase angle are functions of omega. Frequency omega. Functions are frequency omega. Now we go for types of frequency response plots. Types of frequency response plots. So one is polar plots. Two Bode plot. Three log magnitude versus phase plots. Nyquist plot. Polar plots, Bode plot, log magnitude versus phase plot, Nyquist plot. So all are what we have. So one of the other way. There are the sketches of the magnitude and phase angle when we vary the frequency. First one is polar plot. Polar plot is a plot of magnitude. I just call that as a GH. Magnitude GH and angle of GH. I just dropped J omega. Angle GH when omega is varied. omega is varied from 0 to infinity. It's very simple. Polar plot is magnitude and phase angle together. Magnitude and phase angle plot are a locus of magnitude and phase angle when omega is varied from, the frequency is varied from 0 to infinity. So that is called a polar. Then what is Bode plot? Bode plot has a two plots. First one is log magnitude or magnitude in decibels. Magnitude in decibels versus or against log omega with the base 10 log omega plot and phase angle versus log omega plot. Magnitude in decibels or magnitude in dB, same thing is called as a log magnitude. So log magnitude against log. So that is why we need to plot this in the semi-log sheet, right? So x-axis is logarithmic scale. So x-axis is logarithmic scale. Together, magnitude in decibel versus log omega plot as well as phase angle versus log omega plot together, we call that as a Bode plot. Same thing is also termed as a logarithmic plot. Also, it is termed as asymptotic plot or asymptotic plot. We'll see later why that is. So, Bode plot is also termed as logarithmic plot or asymptotic plot. Okay. So differ with this log magnitude again, magnitude in decibel versus phase angle right away is called as a log magnitude versus phase angle. Okay, this is magnitude in decibel, dB versus phase angle plot is called as log magnitude versus phase plot. What is Nyquist plot? So there is a mapping of a Nyquist contour in S plane to GH plane is called as a Nyquist plot. So mapping of Nyquist contour in S plane is called Nyquist contour. Contour in S plane against Nyquist contour in X plane against the Nyquist contour, mapping of Nyquist contour in S plane to GH plane. Okay, GH plane is known as Nyquist plot. Okay, see so again we are all together Nyquist contour in this plane that will be mapped on to the GH plane or G of J omega H of J omega. Then we go for among this, the Bode plot is very popular for the design applications. Okay, design applications in frequency domain. Bode plot is very popular, and we will continue to discuss the Bode. We will take the heading Bode plot. So Bode plot, or it is logarithmic plot, or it is asymptotic plot. So what is that Bode plot? Simply it is magnitude in dB, magnitude in dB versus log omega. Then the second plot is phase angle versus log omega. So it is a magnitude. So what is that we are doing? Again I consider the closed loop system. Let me consider the closed loop system having the forward path transfer function g of s, feedback path transfer function h of s, response in S domain c of s. So we know that overall transfer function C of s by R of s is equal to G of s by 1 plus G of s H of s. G of s H of s. And from overall transfer function, we know that the characteristic equation is given by 1 plus G of s H of s equal to 0. That determines the nature of the response, right? So, characteristic equation of the closed loop system is 1 plus G of s H of s equal to 0. 1 plus G of s H of s is equal to 0. Or we can write this G of s H of s equal to minus 1. G of s H of s equal to minus 1. Wherein G of s H of s is open loop transfer function. Where G of s H of s nothing but open loop transfer function, right? So we now can get the sinusoidal transfer function by putting s is equal to j omega. Put s is equal to j omega. S is equal to j omega. I get g of j omega, h of j omega equal to minus 1. I call this as equation A1. Equation 1. Equation 1 again, g of, so in among us this is nothing but open loop transfer function. So it gives you the condition that the magnitude of this equation 1 is equal to 1 and the angle is 180 degree plus or minus 180 degree. So magnitude magnitude condition of equation 1 is magnitude condition g of j omega h of j omega equal to 1. Let me call this as equation 2. So phase angle condition from equation 1 is angle of g of j omega h of j omega equal to plus or minus 180 degree. Plus or minus 180 degree. So equation 2 and 3 are the conditions. So equation 2 and 3 are useful to sketch the Bode plot. So equation 2 and 3 indicates that absolute and relative stability of the closed loop system can be obtained from open loop transfer function g of j omega h of j omega. So it's very clear that the relative stability or absolute stability says that whether the given system is stable or not. So that is absolute stability. Relative stability, how far it is stable can be determined by the relative stability. Both relative stability and absolute stability can be obtained from the open loop transfer function. Among the frequency domain specification, especially two factors, that is gain margin and phase margin. Gain margin and phase margin determine the absolute and relative stability stability of the closed loop system. Remember that in all the cases we start with open loop transfer function. Our aim is to find the stability of the closed loop transfer function as well as the relative stability, how good the response is from the sketch, right? So absolute stability as well as the relative stability could able to say from the open loop transfer. And for that, let me now consider a general expression for open loop transfer. So let g of s h of s open loop transfer function is expressed as g of s h of s is equal to some k plus of ST Z1, 1 plus of ST Z2 plus so on, 1 plus ST Zm divided by s to the power of n, s to the power of n, 1 plus of STP1, 1 plus of STP2, so on, 1 plus STPn. Now I have considered general transfer function wherein we have m number of zeros and there are n plus n number of poles. So s to the power of n is indicating that n number of poles are there at origin. So n number of poles are there at origin, or it is, so 1 over s always tells you that it is integral factor. So n number of integral factors are there in the transfer function along with the what is called as a simple poles. These are termed as simple poles, right? So now to get the sinusoidal transfer function, we begin with replacing s with j omega. So put s is equal to j omega to obtain sinusoidal transfer function. Sinusoidal transfer function. Sinusoidal transfer function is now g of j omega h of j omega equal to k 1 plus j omega t z1, 1 plus j omega t z2, so on, 1 plus j omega t zm, zm divided by, it is a j omega to the power of n, 1 plus j omega t p1, 1 plus j omega t p2, so on, 1 plus j omega t pn. Now we got the sinusoidal transfer function replacing the s with j omega. Note one more thing, all the factors are in the form of 1 plus some imaginary quantity, 1 plus j omega. This is called as a Bode plot form, right? So this transfer function is in Bode plot form. Okay, this is in Bode plot. You have to express all the simple zeros and poles. And one more, we get quadratic. I will explain that. So should be this one, 1 plus 1 plus 1 plus 0. Not this 1 plus of j. You must express the given transfer function only in this form. It's termed as Bode plot form. After you obtain the Bode plot form, next step is to obtain the magnitude of this antphase. What is magnitude? Let me go for the magnitude of this expression. I hope I have called that as equation 3. So I'll call this as equation 4. Let me call it. So magnitude of equation, magnitude of equation 4 is given by magnitude of equation 4 is given by, that is modulus of g of j omega h of j omega. Note that it's the magnitude of individual factors. It's nothing but the magnitude of individual. What is this? So k, magnitude of this is a gain. K is the gain. K is the gain or constant. K, magnitude of this is, it is the square root of the real part, square of the imaginary part. You need to go on writing that. So it is a square root of 1 square, 1 plus of omega t z1 whole square multiplied by 1 plus omega z t z2 whole square and so on. It is 1 plus omega t zm whole square divided by, it is omega n again root of 1 plus omega t p1 whole square multiplied by root of 1 plus omega t p2 whole square, so on root of 1 plus omega t pn whole square. Let me call this as equation 5. It's very simple now. This gives you the magnitude. Equation 5 gives you magnitude. It is the function of omega. That's all. Same way, phase angle of equation 5 is given by, phase angle of equation 5 is given. So phase angle of g of j omega, angle of g of j omega, h of j omega, it's equal to, note that the phase angle due to each factors you need to take this off. The phase angle due to k is 0, right? So 0 degree, I'll write 0. Phase angle of this one is, so due to the zeros it is plus tan inverse the imaginary part by real part. So more or less it is nothing but the imaginary part, right? Plus of tan inverse of omega t z1. Omega t z1. Very simple to write now. Plus of tan inverse of omega t z2 plus of so on I write here tan inverse of omega t zm. Okay, collect the angle. So it is an addition, right? Addition of the angle contribution due to each factors of the zeros. Then it is the angle contribution of this is j to the power of n. So j is 90. If that goes to numerator, minus j is minus 90, right? So that means it is, you have to take minus, adding all those things, minus 90 n, okay, n degree. If n is equal to only one pole is there, minus 10. Two pole, minus 180. So it goes like that. So minus 90 n degrees is the angle contribution due to the pole at the n number of poles at origin. Then pole due to the simple poles contribute minus tan inverse, if that goes to numerator minus, so angle is Again same thing. Imaginary by real. Imaginary is omega t1. Omega tp1 by 1. So that's all. So again minus tan inverse omega t p2 minus so on minus tan inverse omega tpn. I call this as equation 6. I got now two equations. I could able to get for the given transfer function is very simple now. Express or find the magnitude. So it should be started from here. Get the sinusoidal transfer function. Substituting s is equal to j omega. After that, it should be in the Bode plot form. Bode plot form means it should be always, whether it is 0, simple 0 or simple 4, should be 1 plus something, j something. So it should express in that way. It's called as a Bode plot form, transfer function in Bode plot form. Then I can find the magnitude using equation 5 and the phase angle. Right? Phase angle contribution due to each factor is expressed in equation 6. Now, note that Bode plot is log magnitude. It is not just magnitude. It is a log magnitude. So, how to get log magnitude? Take the logarithm of this magnitude plot means, so in decibels 20 log with base 10. So if I apply 20 log with base 10 both sides, so I will get the magnitude expressed in decibels, or it is a log magnitude. So that is why. So magnitude of equation 5 in decibels is given by magnitude in decibels. So that means it is, I just call this as a g of j omega, h of j omega in dB. I type that one dB. So 20 log I have taken, so I am expressing in dB. This is now equal to, so 20 log with base 10 of this complete magnitude which are expressed as a ratio. So whatever there in the form of a multiplication, they become addition. Whatever there in the denominator, that takes a minus sign. So more or less all the factors now becomes multiplication converted into the addition. How do you go that? So I write straight away the each factor. Instead of taking the 20 log base 10 k. So that's the first. Next, plus of 20 log base 10 root of 1 plus omega t z1 square plus of 20 log base 10 root of 1 plus omega t z2 whole square. I will continue here. So on plus of 20 log root of 1 plus omega t z m whole square. Then the magnitude, this one, it is minus 20 n. So it is 20 or 20 log omega n 20 log with base 10 omega to the power of n, or even you can write that because of the property of log 20 n log omega. Okay, you have to do that. Then I have the other factors like minus 20 log 10 root of 1 plus of omega tp1 whole square minus 20 log 10 root of 1 plus of omega tp2 whole square. So on minus 20 log with this 10 root of 1 plus omega t pn whole square. Let me call this as equation 7. What is this now? So the magnitude is in the form of a multiplication here in equation 5 that has been converted into addition, right? So magnitude has been converted into addition. So now it is very easy for us to draw the factors individually. So the constant can be drawn individually, all the factors, the zeros can be drawn individually, and then the poles can be drawn individually. The pole at origin can be drawn individually, they can be added together to form a sketch. What is that? Sketch magnitude in decibel versus log omega. So, and also using equation 6, we can plot phase angle versus the log omega. This sketch, that is magnitude in decibel versus log omega, using equation 7, and the phase angle versus log omega using equation 6 is known as the Bode plot. So from equation 7 it is clear. So factors can be drawn individually. So there are several factors. The factors can be drawn individually. So write that equation 7 clearly indicates that factors of g of j omega, h of j omega can be drawn individually to obtain magnitude in decibel or dB versus log omega plot. Okay, so factors of j omega can be drawn individually. So to obtain the total magnitude in decibel versus log omega plot. So this is possible. And now the question is, what are the factors? The important factors are now in this one, and we have shown that. So the possibility of constant is there. Yes. A gain or constant is there. Second, the pole at origin, or it is 0 at origin. It can be either pole or 0 at origin. If the pole is there, that is called as an integral factor. If 0 is there, that is called as a derivative factor. Anyway, so pole can be there or 0 can be there. Then first order 0 or pole can be there. Next, quadratic form of pole or zero order. You now is important to see how to sketch the individual factors against the log. Okay, so let me write basic factors of g of j omega h of j omega or basic factors of 1 gain k, gain k or constant k, gain k. Second, integral factors or derivative factors integral factors or derivative factors. They are also termed as poles at origin or zeros at origin. Poles at origin or zeros at origin. So one can exist, not both. Either poles can exist or zeros at origin. So any one form can exist. Usually it is integral, zeros commonly, or then 3 first order factors. First order factors are termed as simple zeros, simple poles. Now you see and simple poles and zeros may exist in the, so first order factors are, so fourth one is quadratic factors. So this is quadratic poles and zeros can exist. There are 4 types here: gain k, integral factors or derivative factors, poles at origin, zeros at origin, first order factors, simple zero poles and zeros exist. Quadratic factors, quadratic poles and zeros can exist. We need to now know how I can sketch the magnitude as well as the base angle of each one. Then we can add them together according to equation 7. Here can sketch it individually and then we can add. Or we need to know the magnitude contribution of each factor can be tabled. The contribution of the magnitude due to each factor, then they can be, you can sketch that together also. So we will need to know that. First I go for the gain k. Gain k. Let g of s is equal to k. Some k. Let g of s is equal to j. Okay, I have only one constant, so again put s is equal to j omega to time the sinusoidal transfer function. Same thing. I'll get g of j omega is equal to k. J of j omega is equal to k. Magnitude of this j of j omega is equal to k. Phase angle of this j of j omega is equal to 0. Will not contribute 0 degree. So magnitude in decibels or dB, magnitude in dB. Magnitude in dB, I always call this as G of j omega dB. G of j omega dB is equal to 20 log k base 10. Now it is very simple now. If k is equal to 1, take your calculator and see that G of j omega dB is equal to 0. If k equal to 10, so this G of j omega dB, it is equal to this log 10 is equal to 1, so it is 20 dB. 20 dB. And so can calculate that. Okay. So what is now? I have to now go for the sketch. I now see that take your log sheet. I have now sketched this one against the frequency. I call 0 dB line, so gain in dB, or modulus J of j omega dB. Gain in dB, 0 dB line. Then I have, so say the frequencies, it is against log omega. What is that? For k is equal to 1, it is 0. What is the slope of this one? Slope of this is very important. Slope is very important. So if I differentiate this with respect to log omega, it gives you the slope. If differentiate this with respect to log omega, you will get a slope. So log omega is very much similar to your x. So this is in the form of y is equal to mx plus c. Wherein here I don't have log omega terms. So this is 0. So I have now y equal to c form. So if I differentiate this, you will get the slope equal to 0. So slope, so this represents your straight line. Okay, equation 8. Equation 8 is a straight line. Equation 8 is a straight line with slope 0 dB per decade. I will tell you what is this. It is very important. I will tell you what it is. Okay, 0 dB per decade. Why it is 0 dB? If I differentiate this with log omega. So what is that? D of G of j omega by D log omega. Log omega you can take it as x. So you will get 0. Right? What is that? 0 dB means it's horizontal. So the line will go is horizontal line 0 dB per decade for k equal to 1. For k equal to 1, this is your plot. For k equal to 10, it is 20. Suppose I have a line, so it is 20 dB. So you have a minus 20 dB. If you mark like this, so for k is equal to 10, it is the line 0 dB. Phase angle is, what is phase angle? So phase angle 0. Phase angle is contribution of this is 0. Suppose I have a 0 degree. So this is for all the gain k equal to 1, 10, so on. It's equal to 0. So it's very simple now. So next comes, let me go for the second. What is it? This is 2 integral factors. I'll go for integral and derivatives separately. I'll go for integral factor. Integral factors are pole at origin. Integral factor or pole at origin. So number of pole, suppose n number if I have. So let us integrate. Let g of s is equal to, it is 1 over s to the power of n. N number of poles at origin. So generally, then let us derive general and we will talk about the one pole at origin, 2 pole at origin, more or less in the example 3 pole. Anyway, n number of poles are at origin. What is your, again same thing. What s is equal to? S is equal to j omega. To obtain the sinusoidal transformation, you will get g of j omega equal to 1 over j omega to the power of n. J omega to the power of n. Okay. What is now the magnitude of this? G of j, magnitude of g of j omega is given by g of j omega equal to 1 over omega to the power of n. Magnitude is thus, this phase angle of this g of j omega equal to, as I said, j contributes denominator, so if that goes to numerator, minus 90, because of n number, minus 90 n. So minus 90 n contributes minus 90 n degrees. Okay, so now take the magnitude in decimal. Magnitude in dB, g of j omega dB. It is 20 log 1 minus of, it is 20 log 1 minus of 20 n log omega is base 10. So I will take 20 log omega to the power of n by the root of log. It can be written 20 n log omega. So this log 1 is 0. It is simply written minus 20 n log omega base 10. I call this as equation 10. Equation 10 is a equation of a straight line, y equal to mx, where x is equal to log omega is base 10. Okay, so the obviously you are telling that the remaining 20n is your slope, or slope, write that equation 10 represents a straight line. Equation 10 represents a straight line, and slope is very important. Slope of the straight line is very important in the Bode plot. Should remember this. What is the slope? So how do you get? So D, differentiate this with respect to log omega, differentiate equation 10 with respect to log omega, differentiate equation 10 with respect to log omega base 10. I'll get it is a D of G of J omega H of J omega divided by D of log omega with base 10. Remember, this gives you minus 20n. What is this unit? Minus 20n. The unit of this is change in gain divided by change in gain in dB divided by this is change in frequency. So the unit of this is dB per decade. Okay, the slope of the line is minus 20 n dB per decade. If n equal to 1, if n equal to 1, that means only one pole at origin or only one factor at origin, 1 by s. If n equal to 1, then slope equal to minus 20 dB per decade. Minus 20 dB per decade. If there are two poles, n equal to 2, slope equal to minus 40 dB per decade. N equal to 3, slope is equal to minus 60 dB per decade. That's so on. More or less, you may get one pole at origin, so then it is minus 20 dB. You need to remember this. This is very important. Slope is very important. If it is 1, straight away you have to take this minus 20 dB per decade. That's why I am telling you. Minus 20 dB per decade. If two poles are there at origin, so that is in the denominator, minus 40 dB per decade. 3 are there, minus 60 dB per decade. Okay. Now let me come to this one. What is this? I said that change in gain in dB divided by change in frequency. Change in gain in dB by change in frequency. Suppose if there are, so I call this as unit gain. So 1 dB per decade. So unit gain equal to unit gain. Let me see what it is. Unit gain. Unit gain means 1 dB per decade. So 1 dB per decade. Suppose for 1 dB per decade, change in gain is 1. So 1 minus of 0, change in gain. Okay, change in gain is 1 dB minus of 0. Then change in frequency is log omega 2 by omega 1. Log omega 2 by omega 1. So that means I get now, there are a lot of things, but it is very, very simple if you understand, right? So we are going with the basics, right? I am not simply going straight away to the some people do the slope and then simply plot, but you don't know how that slope arrived. Slope arrived, and what is that? You never know. What is this state? You never know. See, this is how it comes. So slope is change in gain and change in frequency. equal to unit gain is 1 dB per decade. So which means change in gain is 1 with respect to what is this frequency we are calculating. So our log omega 2 by omega 1 equal to 1, or omega with base 10, omega 2 by omega 1 equal to 10 power 1, or omega 2 is equal to 10. Note that this is called as a decay. Change in frequency 10 times to the previous frequency is called decay. 1 unit of gain, okay, 1 unit of gain change with respect to change in frequency 10 times is known as the dB per decade. 1 dB per decade mean to say that, so change in gain is 1 dB with respect to what? Change in frequency of 10 times with respect to the previous. That is why, so when I have to now sketch, go for a sketch. That is why while plotting this, I will now go for the sketch. What is that? Note that since this is logarithmic plot, don't start at any point of time with 0. Don't write 0. The log of 0 is indeterminate. Don't start with log 0. It should be started with some starting frequency. I will tell you how to start that one. It should be with some starting frequency. Now, if the starting frequency is 1, then next frequency log omega, this it is 10 times. Okay, because I have to sketch the gain with respect to decay 10 times. So 10 times of that is 100, 10 times of that is 1000, like that. You have to take the frequency, starting frequency, if it is 1, then 10 times of that, 10 times of the previous one. Now, gain is plotted now. Gain in dB here, so 0 dB. So always go for this. And now do this one. With your scale do this, and later we will see this. 20 dB, 40 dB here, minus 20 dB, minus 40 dB. Okay? So I will go for a magnitude plot. What is that he is telling? For a one pole at origin, the slope is minus 20 dB. This is telling that it is a straight line. This equation is a straight line. With what slope? Minus 20 dB per decade. How to plot it? It is very simple. So it is telling you that change in gain is minus 20 with respect to change in frequency of 10 times. So start here. Change in gain is go down minus 20. Change in gain is minus 20. Right? So change in frequency is 1 to 10. So mark that. Mark that. This is very, very important. So first thing is, in the semi-log sheet, before that you need to know what is this minus 20 dB per decade, minus 40, minus 60. What do you mean by that? How to sketch? This is very, very important. The entire Bode plot, so sketch of Bode plot depends on this one. Knowing the slope of that straight line. More or less, almost all the factors involved with this y equal to mx form, except your gain constant, more or less all are in the form of y equal to mx form. So x is log omega, m is something. That m is very, very important. That slope is very, very important and must know how to sketch. So how do you do this? So point here, minus 20, go there. So 10 times of that. If I join that, so that line may go somewhere, so that forms you minus 20 dB per decade line. minus 20 dB. Don't write dB. Decade. Slope must be written dB per decade. If it is gain, it becomes a stride. Minus 20 dB per decade. So use your scale and do it properly. Next. This is what? This is for what? 1 over j omega. This is the sketch for 1 over j omega. If I have one pole at origin. Next. If I have a two pole, that means 1 by j omega square, it is minus 40 dB per decade. What do you mean by that? So go down minus 40. 10 times of that is this. Join to these two lines. Okay, this is the whole line. So write minus 40 dB per decade. So it is 1 over j omega to the power of 2 or 1 over s square. Even you can write it 1 over j omega square. That's minus 40 dB per decade. How do you go for this? Again, so one more. If you want 60, mark that one. So it is minus 60 down. So it is from 0. I will now plot. The line joining these two gives you minus 60 dB per decade, and that is for 1 over j omega cube. Okay. I hope you understand that. Is it clear? Is it clear? So how to sketch the straight line? So all are approximated into straight line. That is why they are called as a asymptotic plot, right? So in Bode plot, actual curve is a smooth curve, but they are plotted with the straight line, fitted with a straight line. They are the tangent to the actual curve, so that is why they are called as asymptotic plot. So Bode plot, moreover, approximation of a quite good approximation of your actual plot, and which give you very much accurate results and quick enough. So that is why Bode plot is very popular, right? Bode plot is very popular among all these plots. So you should know how to sketch the line first. So minus 20 dB per decade, 40 dB, minus 60 dB. These are for one pole at origin, pole at two poles at origin, three poles at origin. Okay. What next? I have then the phase angle. Phase angle is more or less, in this case, I will separately write the phase angle. If I have a 0 degree, minus 90, minus 180 degree, and so on. So again it is log omega. Same, you have to plot it in the same sheet. So magnitude plot at the top, and below that you have to sketch the phase angle plot. You should plot both of them together, one above and another below that. Again, I am showing separately anyway, right? So here, corresponding to the pole at origin, it is minus 9. Phase angle g of j omega, h of j omega is equal to minus 90 when n equal to 1. So one pole at origin, minus 90. So when n equal to 2, I call simply gh is minus 180 degree. when n equal to 3, angle of g of h equal to minus 270. So it's very simple. Angle is 18 minus 90 contribution, individual contribution. So when it is two poles are there at origin, so 180 degree. So you can sketch that. So that means it is a straight line here. So this is for so 1 over j omega. So 180 degree from all the frequencies 110, 100 times. So it is 1 over j omega square. It is minus 270 for 1 over j omega whole square. Okay, I hope you got that. See now. Derivative factors. I will quickly do this. Derivative factor. So derivative factor means zeros at the origin. Okay, that means g of x, it is in this form. G of x is equal to s to the power of, say, I'll take m. S to the power of m. So again, put s is equal to j omega. You will get g of j omega equal to j omega to the power of m. I'll assume m number of zeros are. So this is R factor. So integral factors may be there, or your zeros may be there. If I have a zero, then it is given by this. So g of j omega, magnitude is omega m, phase angle of this gh is equal to plus 90 m. Plus 90 m. Then g of j omega in dB, magnitude in dB. This is magnitude in dB. It is given by, it is 20 m log omega. Note that this is once again in the form of y equal to mx. Okay, wherein this is your x, this is your slope. So easily you can write that one. So differentiating with respect to log omega, you will get 20 m as the slope, plus 20. Slope of this one is also representing a straight line. Let me call this as 11. 11 represents a straight line. All represent straight line, right? Fitted with a straight line. So with the log omega as the variable in x-axis, right? So 20 slope is equal to 20 m dB per decade. So when m equal to 1 means 1 0 is there. So that means it is j of j omega is equal to j omega. So 1 0 is there, then slope equal to 20 dB per decade. Then when two poles are there, which means j of j omega equal to j omega square, slope equal to 40 dB plus 40 dB per decade. can understand. So if I have a derivative there, instead of a 0, then it will be plus 20 dB per decade, plus 40 dB per decade in case of a 2 zeros, with a final contribution of 90 plus 180 and so on. M equal to what? 90. M equal to 2, 180 and so on. Now what is that? Same step I will do this. So I will now go for the plot. Now similarly you can do this one. 20 dB per decade means go above 20. 0. Change in gain is plus 20. Change in frequency is 10 times. You can plot anywhere. Remember that. It can be plotted anywhere. Right? Change in frequency 10 times. Mark those two. And if I join this will be 20 plus 20 dB per decade. Plus 20 dB per decade line. You can draw this one for j omega to the power of 1 plus 1. Sorry? Yeah. Then I have next with the 40 dB per decade. So changing gain is 40. 10 times is this. To draw that, it is plus 40 dB per decade for your j omega to the power of 1. J omega square, okay, like that. It goes like for if I have a 6 plus 60 dB per. Need to remember, very simple. Need to remember slope. That's all, right? Need to remember just the slope, and then it gives you. It is nothing but a straight line. You need to plot that together. How to plot we will see. So you should now at last need to remember only this. Plus 20, 40 if I have a 1 polar top, 0 star is a 2 polar, 0 star. 1 pole minus 20 minus 40 minus. That's all. Okay, we will see. Enter some more. Okay. Now, same way, here the angle contribution is, it is 90 degree. This is for j omega. It is 180 degree. 180 degree. So there I get a j omega square and so on. Yes, we have now completed the second, that is the integral factor and the derivative factor. Another important thing here is initial line. Initial line is always due to the gain k and integral factor or derivative factor. Right? The initial line is always because of gain k and integral factors or derivative factors. Integral factors or derivative factors only. Let me go for one important thing. Need to remember for I assume that j of s is equal to k divided by s to the power of n. Equally can be, if that goes to numerator, it is s to the power of minus n plus or minus. If I do that, becomes for derivative factor also. So right. So what is this? So if n number of poles at origin, n number of poles at origin, put s is equal to j omega, g of j omega equal to k by j omega to the power of n. Magnitude in dB, that is g of j omega dB, or even h of j omega. If it is unity feedback, then it is 1. So that equally valid for that. Gain in dB can express, there are two factors, magnitude is k by omega n. Now can be 20 log k with base 10 minus of 20 n log omega. So this is the equation for the gaining dB due to the initial line. The contribution is because of the gain as well as the polar charge. Now if I have a zero charge origin, this becomes plus. This becomes plus. So here you can take plus for zeros at origin, minus for poles at origin. Okay? Minus for poles at origin. This initial line passes through the 0 dB line, because when I take the 20 log of the gain, so that is g of h equal to 1. If I take the magnitude in dB, this becomes gh dB equal to 0. So this is very important. Note gh dB equal to 0 in the log magnitude. So that means the condition is that for closed loop system, stability can be analyzed with respect to 0 dB line. There the stability is analyzed in this case with respect to minus 1 J0 critical point, that is called as a critical point. Now 0 dB line is called as a critical point. So relative stability as well as absolute stability is now discussed with respect to 0 dB line and minus 180 degree in the phase angle. 0 dB line and phase angle, we know that it is plus or minus 180. So the relative stability is now stated in the Bode plot with respect to 0 dB line. So because when I take the decimal, this becomes log, that is 20 log 1 is equal to 0. So 0 dB line comes into picture. Yes. Now we must know where the initial line touches the 0 dB line. Where it touches the 0 dB line. So when the initial line touches the 0 dB line, this becomes 0. Right? So now you will get the condition substituting the 0 here. Write that. So initial line touches 0 dB line. Initial line touches 0 dB line. At certain frequency where gain in dB equal to 0. Gain in dB equal to 0. Substitute that in this expression. I'll get 0, 20 log k. I'll go for first the integral factor minus 20 log base 10 omega. I'll take n to the power of omega n. Okay. So 20 log k minus 20 log omega to the power of n, or it is 20 log 10k equal to 20 log omega n. So then 20 log omega n, taking anti-logarithm. So it k equal to omega n, k equal to omega to the power of n, or omega equal to n to k to the power of 1 by n. K to the power of 1 by n. Very, very important. This is one of the key factor here. Now note that when n equal to 1, one pole is there. So initial line meet the 0 dB line at omega equal to k. In your transfer function, this you can know what is k. So at that point it meets. When n equal to 2, it meets at root of k. When n equal to 3, it meets at cube root of k, and so on. If I am repeating that, so it's very important. I am repeating 0 initial line meets your 0 dB line corresponding to omega equal to k. If there is one polar origin, that means it is g of s equal to 1 over s. If two poles are there at origin, that is integral factors are 2, then it is square root of k. If 3 are there, g of s is equal to 1 over s cube, then it is cube root of k. Instead of pole, if I have a 0, this becomes plus, then I get the k equal to omega to the power of minus n, or it is 1 over k equal to omega n equal to 1 over k. So omega is equal to 1 over k to the power of 1 by n. If 0 is there at origin, 0 is there at origin, s to the power of 1, so and then omega intersects 0 dB line at 1 by k. So n equal to, for n equal to 1. So 1 0 at origin, then 1 by k. Or if n equal to 2, if n equal to 2, omega is equal to 1 by root k. 1 by root k, so more or less this is. So thus you need to remember. So if I have one pole at origin, the 0 initial line meets 0 dB line at omega is equal to k, and 2, then it is root k, 3 cube root of k. Same way, 1 0, 1 by k, 201 by root k, 301 by cube root of k. Got? Right? That's the integral factor. I hope you understand how to sketch the slope of a line. So corresponding to the polar origin, one polar origin, two polar origin, three pole, zero origin, and of course 0, 2 zeros at origin. Also the phase angle plot is very simple. Whatever the angle you have to plot on. So I go to the third and then we will see the rest later. So we will go to the, what is that? First order factor. First order factor. First order factor, they are also called as simple pole and zero. Simple poles and zero. Usually these occur more than twice or zero. Combination of zeros and poles may be there, as well as maybe sometimes poles and so on. Right? So simple poles and zeros and derived together, they are in this form, that G of S is equal to 1 over 1 plus ST. ST, or it is, and this is simple pole, simple zero, maybe in this form, G of S is equal to 1 plus ST. Simple pole is, it should be in the form 1 plus ST, some t is some constant. Here also 0, 1 plus ST, t is some constant. And together I can write this one as G of S is equal to 1 plus ST to the power of plus or minus 1. Plus for 0, minus for 2. Plus for 0, minus for 4. We'll derive together this one, right? Now, put S is equal to J omega. I'll get G of J omega equal to 1 plus J omega t to the power of plus or minus 1. To the power of S or minus 1. What is now? The magnitude is G of J omega is equal to, the magnitude is now, it is 1 plus omega t square plus or minus 1. Plus or minus 1. And phase angle G of J omega, this is magnitude. Phase angle is, it is plus or minus tan inverse of omega t. Again plus for 0, minus for 4, right? Plus for 0, minus for 4. Here 1 plus omega t square, so not this plus for 0, minus for 4. Now, magnitude in dB, magnitude in dB, magnitude in dB, g of j omega, of course, if it is unity, g of j omega, h of j omega in decibels is equal to, it is plus or minus 20 log 20 plus or minus root of, suppose if it is 1 plus j omega t, it is plus 20 log root of 1 omega. So because of 1 by log 1 is 0, minus of 20 log of this magnitude, root of 1, right here, I left square root here, square root of 1 plus omega t square plus or minus 1. So yes. Now to represent this with a straight line, we will take that for lower frequencies, omega t is far less than 1. For lower frequency, omega t is far less than 1. So remember that, then this is negligible, this becomes root of 1, log 1 is 0. So my straight line becomes 0 dB, 0 dB. This is very important. I'll call this as A. For lower frequencies, my straight line is simply 0 dB. Same way for higher frequencies, omega t is far greater than 1, very greater than 1. 1 is negligible, so root of omega t square becomes omega t. So then this is g of j omega dB is equal to 20 log base times omega t. I call this as B. Note that, so this is equal to omega can be written log omega plus of log omega t. T is a constant anyway. If I differentiate this with respect to log omega, again the slope is plus 20 dB per decade. The slope of B, slope of equation B, so is equal to, plus or minus, I left that one, plus or minus is that, plus or minus 20 dB per decade, plus or minus 20 dB per decade. So for a simple 0, it has a slope of plus 20 dB per decade. For simple pole, it has a slope of minus 20 dB per decade. It's very important. So for simple 0, slope equal to plus 20 dB per decade. For simple pole, slope equal to minus 20 dB per decade. What is that? So this is representing a straight line. Equation B. is a straight line. Equation B is a straight line with the slope plus 20 dB for a simple 0, minus 20 dB per decade for simple pole. Always, whatever may be the value of t, irrespective of value of t, it has a fixed slope of minus 20 if it is a pole, plus 20 if it is a 0. Okay. And note that this is very important. Another line is there where it is with a 0. So simple 0 and simple pole, they have, unlike the initial line, it starts with a very small frequency up to the large frequency it takes. But the simple 0 and simple pole is not so. It has two lines, 0 dB line as well as line with plus or minus 20 dB per decade. Right there. Simple pole and simple zeros, simple poles and simple zeros have two lines with 0 dB per decade slope, 0 dB per decade slope, and plus or minus 20 dB per decade, plus or minus 20 dB per decade. I hope you understand this. Minus for your pole, plus for 0. Now, the frequency at which these two lines meet is known as corner frequency. Right there. The frequency at which 0 dB line, 0 dB per decade line, frequency at which 0 dB per decade line and plus or minus 20 dB per decade line, 0 dB per decade line and plus or minus 20 dB per decade line meets is known as corner frequency. Corner frequency and denoted by WC. And denoted by WC. Denoted by WC. And now, where they meet? So, they meet when they intersect with each other. So, equal equation A and B. Equal equation A and B to find corner frequency. So equating these two, that means 0 equal to plus or minus 20 log omega t plus or minus log omega t, or it is equal to 20, so log omega t equal to 10 power 0, it is equal to 1 omega c, this is equal to omega c equal to 1 over t. Two lines. See, it is very simple now. If I have a format 1 plus say omega t, reciprocal of this omega, that's a constant. Reciprocal of that omega gives you the corner frequency. There the 0 dB line and the plus or minus 20 dB line meets. So that's very important. So write that one. 0 dB per decade line, 0 dB per decade line and plus or minus 20 dB per decade line meets at omega c equal to 1 by t radians per second. omega t equal to take this and then it's again I call that zero gain in dB. I start with the frequency 0.1 by t. Okay, 0.1 by t, 1 by t, it is 10 by t and so on. Okay. So it is telling you that the one pole, so it is g of j omega. If I have this 1 plus j omega t, right? So this is having a corner frequency of 1 by t, right? So this is having a slope of minus 20 dB per decade. Till 1 by t, it is having 0 dB line. So mark 0 dB line till 1 by t. So this is 0 dB per decade line. So 0 dB per decade line till 120. Now you remember, the previous, they do not have any corner frequency, it is a one single line, initial line. But now, should be careful, you have two lines, one with 0 dB per decade, another with plus or minus. Minus for pole, plus for zero. What is for pole? Minus 0 dB till that corner frequency. This corner frequency, suppose if it is 1 radian per second. If it is 2, 1 t is 2, 1 by 2 is 0.5, so on. Right? Then I have a minus 20 dB. So generate minus 20. So minus 20 down 10 times. So this is your minus 20 dB decay line. This is the sketch for 1 plus of or easily j omega t to the power of minus 1. Okay, for a pole. For a zero, reverse. So it is for j of j omega 1 plus j omega t. Remember this t will vary. If I have more than 1 0, simple 0, this t will vary. It depends on your transfer function. Now, how to sketch? Till this point, it is 0 dB. Next, plus 20, your changing frequency 10 times. Plus 20 dB per decade. It is always, remember, first order factor, pole, always has the slope of minus 30 dB per decade only. Nothing other than that. It has two things. 0 dB line as well as the minus dB per decade line. It has a corner. You need to remember only that. Slope, two lines. It has two lines. Means at a corner frequency that is given by 1 by t. Then 0, simple 0. Always it is plus 20 dB per decade. Nothing other than that. Okay. So I think that's a sketch for your simple pole or a first order factor or a simple zero or a first order zero which is having corner.